Let's move to the next set of talks. The next 4 talks will be something that you usually hear lab reports, but this year, this meeting, we asked the presenters to focus specifically on the operations in the laboratories that automate data validation, verification, and submission, and improve data quality and timescale generation. So first speaker, I would like to welcome Diego, please, to share your screen for the presentation.
Thank you, Marina. I will share my screen. I hope you can see it now. Okay, thank you. I will start. First of all, thank you for the possibility for sharing this presentation with you. Good morning to everyone. My name is Diego Luna. I work at INTI, the National Metrology Institute of Argentina. And what I'm going to talk with you about is about data validation in the UTC and rapid UTC submissions that we make at INTI. Well, I will first explain, I will show you how the laboratory's setup is organized. Then I will show you how our internal measurement system is made and how we check the clock's performance in an internal way internally in the laboratory. And then I will show you how we make some kind of validation of our measurements by comparing our clocks to different clocks in the same country that do not contribute to UTC, and finally some concluding remarks. So this is the room of the receivers. Here we see the 3 clocks we have and the different receivers we use and some other measurement hardware. The daily submissions of INTI to UTC and UTCR generations are GPS data. We only have GPS, and we use for that purpose a GTR50 receiver, and we report RINIX and with code measurement and phase measurements corrected by ionospheric delays. And we also provide a time difference between the 3 clocks we have. We have 3 commercial cesium clocks, and we make these measurements using a Stanford Research time interval counter. So a short description of our lab can be seen in these slides. We use the 3 clocks we have, and associated to the first cesium clock, we have a few receivers connected to them. And in our case, UTC INTI is defined here at the output of the GPS distribution system. And okay, I will go into detail of the different parts of the laboratory, but the first things we do is to measure the ambient conditions in the laboratory. We measure, as usual, temperature, humidity, and pressure in a permanent way, 24 hours a day. And I will first start to describe this measurement system, which consists of the 3 clocks, a multiplexer, and the time interval counter. And I will shortly explain you how we do that. Here we have there is one personal computer that controls use via USB and multiplexer that changes between the pulse coming from clock 2 and clock 3, and that signal is fed into the channel B of the interval counter, while in channel A we always are receiving the the pulse per second of clock 1. The same computer controls the counter and takes the measurement and generates the report that we send via FTP to the VIPM. I won't go much into detail about the format of the file and the other cares that have to be taken into account, because in the next talk, Oscar Fallas from ICE will explain this in a more detailed way. I will just mention that the multiplexer we use is homemade, it was quite cheap to build. It's built only with an Arduino card and a few relays. We had some doubts at the beginning when we built this multiplexer because of, you know, the impedances in here, the income and the output, but we measured the shape of the pulses before and after the multiplexer, and we noticed that there were no distortion in the shapes of the pulses, so we adapted the system and we use it in a permanent way. The measurement system, the software for the control the measurement system was written in LabVIEW until the last year. So, and last year the computer went broke, so we had to program everything again, and we thought it was a good opportunity to rewrite all the software in using a different language. So we code everything in Python. The control and the reports are made using the code we made. It's quite simple. There are about 100 lines of code. If you need it, you can ask for me and I can share it with you, no problem. So with this system, we permanent measure the time difference, for example, between cesium 2 and cesium 1 and cesium 3 and cesium 2. And we make the usual calculus using with a lambda deviation and three-cornered hat. So as I explained to you at the beginning, the part of the hardware we use to submit to UTC and UTCR is all this that I show in here, that is shaded in here. But to have a better control of our system, we use a tool that here I show in here that is based on the GPA, on the SIM time network. SIM is the Inter-American Metrology System. We have a GPS receiver, which is associated to the clock number 1, and we contribute to the time and frequency network in SIM. That is a real-time measurement system where we can control the time, we can see the time difference between our clock and the clock of any country in the SIM region in almost real time with only a 10-minute delay. It's a great tool for checking the behavior of our clock. Sorry. On the other side, we also use another receiver that we have to make remote comparisons with other clocks, but inside the country. Here in Argentina, there are many laboratories, but we collaborate with other time and frequency laboratories that do contribute to UTC. For example, the Instituto Geográfico Nacional, the National Geographical Institute, and AGO, which is a geodetic observatory, which are all located nearby the city of Buenos Aires. So with them, we collaborate to compare our clocks. And you can see here, for example, the time difference between GPS and clock 1 of INTI, and the same measurement with a different receiver, sorry. This is the receiver we use to contribute to UTC, and this is another receiver we use to internally check our measurements. And you can see, for example, in here, you can see a peak in here. And as the same peak does not appear here in this graph, we can see that there was a problem with the receiver and not with the clock. And of course, we also, on the side of, we made the same measurements with other laboratories, here AGO and Geographical, the other clock. And we also make common view measurements with the other laboratories to check our clocks. We call this initiative Red Nacional de Tiempo. It's a national time network. We work on it. And we also calculate, for example, the Allen deviation of the clocks. And all this information is stored in a public FTP where everyone can access, not only the laboratories, anyone is free access. And we have some other reports that are automatically generated. For example, we generate relative offset frequencies, for example, in nanoseconds per day or in a relative way. So that's another tool we use to validate our measurements and to control the other systems. So as a concluding remark, what we do is we try to check the measurements in as many independent ways as possible, as I just mentioned. And another conclusion we have is that measurement automation is crucial in time and frequency. Of course, you cannot be 27 days a week making measurements in a laboratory, but there is always a need for a final inspection of the data that has to be done. And okay, and that's all what I wanted to share with you. If you have any doubts, any questions, feel free to contact me. My email is down here, luna@inti.gov.ar. So that's all I wanted to share with you. Thank you everyone for listening.
Thank you very much, Diego. Very, very good presentation. And I'm sure there will be follow-up questions to you personally, maybe on sharing the software tools or the design ideas. I really like the fact that you operate a public FTP site where all the measurement information is available. That's, I think, a great idea for other labs to maybe implement, especially as Patricia mentioned in the beginning, as we're all moving to the fair and accessible data and public data. So that's a great start. Thank you very much, Diego. I don't see any questions, so I will now ask Oscar, please, to share his screen and start his presentation. Thank you.
Hello. Hello, Marina. Do you see my presentation? Okay, thank you. Well, hello, all colleagues. For me, it's a pleasure to be here. Thank you for the invitation. My name is Oscar Fallas Cordero. I work at Instituto Costarricense de Electricidad, ICE, which is the designated institute for time and frequency in Costa Rica. Today, I'm going to present to you how or our automatized control system for VIPN data submission. We will go into these topics. First, I'm going to present you a general configuration and connections to understand how we have our setup configuration. Then we are going to the UTC and UTCR submission that we do in automatized way. After, we will go to the monitoring, the cesium parameters and environmental conditions that we realize in our lab, and the control system performance for quality, data, and accuracy, and some final conclusions. Well, here we can see the very general schematic of our system. In this step phaser output is where we define our UTC. We take this signal to our 1PPS distributor to send different signals, for example, to our time transfer systems. And also, we take this signal to our frequency counters that we use to compare the 1 PPS against the 1 PPS of our clocks in an automatized way. I'm going to details in the of this in the next slides. Also, we have through serial connection communication with the systems to get the operation parameter and evaluate the behavior of the internal clocks. Okay, the time signal comparison, a little bit more detail. As I already mentioned, we have 3 synthesized frequency counters that are commercial counters. They are connected through GPIB interface and to a computer. The computer is the time is adjusted by our INTP servers for the time stamp, and in the computer is running a very simple program that takes the time difference between the 1 PPS coming from the distributor and the clock 1 PPS signal. These values are saved in a daily file. We measure this once a second, and the program save the difference between each signal and the clock and save it as we can see here, the MGD file, the timestamp, and the difference without correction. This is very important because these are raw data. We have separated as we can see in the next slides. We use this file with this data. How? Well, there is another software running in the same computer to avoid problem, but it's independently to avoid problem with the measurement and the process. That this program, what do is to consider all the delays correction needed to get the final difference between the UTC and the clocks. As you can see here, we take into consideration the delay of the cable coming from the state phaser to the distributor, the cable delays from the distributor to each frequency counter, the output delay of the distributor, each channel, and also the cable delay for the cable from the system to the counter. Also, the VIPN lab code is considered, and VIPN clock codes, and what the program do is the follow. At the beginning of the day, the program gets the data and correct the values and prepare an ASCII file as follow. Following the VIPM rules, it generates the file considering the MGDI, the VIPM lab code, the VIPM clock code, and the difference that now is applying all the correction. And the same is for the other 2 clocks. And after that, the programs consider the information given by the VIPN of the password, the username, the IP, and the direction, and upload daily the file to the VIPN FTP server, and also send us a confirmation email with the raw data and with the daily file created for us to confirm and see the information. A pretty similar routine is for the UTC submission with a couple of differences. First, this routine runs the first day of the month, and what it do is that looks for the days of the month before and lookups for the 4 and 9 MGD ending days, takes that data from the raw data, applies again the correction, and create the file following the same structure from the VIPM. The program after that, changing only the direction for the UTC, runs again and upload monthly the ASCII file to the VPN server and send us a confirmation email to evaluate also the monthly file and the raw data. Well, also this software is in LabVIEW, and I think it's no problem to share with you if you need it. so we can contact me later. Regarding the operation parameters monitoring that I already mentioned, we do in another computer a very simple program that just use the serial interface to ask the operation parameter for each clock. What we do here is that, for example, for the 5078 cesium, we ask for the oven information, the C field, E mode, gain, power, temperature, and for other models, similar value to generate the graph of the operation parameters. In this, we plot the maximum, the minimum limits according to the manufacturer value, and compare with the result that we get from our cesiums to see the health of the clocks. To complement that, we also do environmental monitoring measurements continuously. For example, this program is showing you the measure that we do for temperature, humidity, and pressure. In here, we configure where we can save the data. We save one every minute. Also, we can configure the information for a weekly report. This sends a plot of the program and also some summarized information that we use to evaluate, for example, the maximum, the minimum, the media, standard deviation to see how the conditions are going. Visible and audible alarms are configured in the lab, and also an email in the case of an event alarm is sent to us if any value gets out of the control limits that we defined in the software. Also, if the equipment is measured, we can apply some correction to get the final value. With that, we try to use it to complement and evaluate the quality and accuracy of our cesium and doing a behavior analysis. For example, in the software, we can see the slope corresponding to the frequency adjustment that we apply in the phase generator. Also, we can see the relative values between the three clocks. And in a long term, we can see the same information, but for different average time. For example, we can see 10 seconds, 100 seconds, 1 hour, 1 day, even 5 days. And we use this information to evaluate through Triconehat method and Allen deviation, the absolute stability for the clocks. As my colleague, Dr. Diego already mentioned, we can complement this work using for the quality control, using our SynTime network. In here, I'm presenting you, for example, the information that we can get in this comparison against NIST. We can see frequency offsets, we can see Allen deviation, we can see different data that, and also, as Aurelie presented, we can get information from the BIPN time database. In here, I'm presenting you the information from the interactive plots. In this, we can evaluate how our UTC is going in relation with the UTC. And this plot is very useful for us because we can compare the result of both systems to see how good and how healthy is our realization of the UTC. So finally, we can conclude that a functional automatized internal system for UTC submission can be developed using low-cost commercial solutions. We can use open or free software and very cheap equipment. Monitoring environmental conditions and operation parameters can be very useful for determining cesium behavior and event correlation. In the daily maintenance, this is a very important tool to have in consider. And finally, the UTC and UTCR reports provides two valuable information for contribute to the BIPM task and the NMI and designated institute time realization maintenance and develop, which is very important for the community. Well, with this, I hope I encourage you to start contributing, and feel free to contact me if you want any software or any additional information. And again, thank you for the invitation and for considering our work. That's all.
Thank you very much, Oscar, for your presentation. Great work. I like that you mentioned automatic email notification system that you implemented. I think that's the key. Otherwise, we'll not be able to leave our labs ever and monitor the performance of the systems. So in addition to environmental conditions monitoring with email alerts, probably alerts can be sent if clock offsets get out of certain threshold levels, or GPS measurement results show some abnormal behavior. I think that's an excellent system. Thank you very much, Oscar.
You're welcome. Thank you.
I don't see any questions, so that's a reminder. There is a way to ask questions. Please use the hand tool in the system. But for now, I will invite Filippo to give us the next presentation.
Thank you, Marina. I will, I have to share my screen. Can you see my screen? Can you hear me?
Yes, yeah, we can see your screen and hear you. Thank you.
Yes, both.
You can see also my screen? Yes? Okay. Let's see if I can make it a little bit larger. I know there is a way to make the full screen, but I maybe. Okay, can you see enough? It's large enough, the screen on you. Okay, so I will present a full automation generation of Italian timescale UTC ET. And this work is done by myself, Ilaria Sesia, Giovanna Signorila, and Andrea Perucca. So Italian timescale UTC ET since more than 1 year now is generating using a fully automated procedure developed in-house at our institute. Most of the results I present were published in or presented in a conference, so I have reported where you can find the relevant reference during this presentation. So the performance of UTC ET are satisfactory. So we were able to, during this last year, essentially, we were able to maintain the time scale within 4 nanoseconds and 95% of the time, demonstrating a stable and accurate realization of UTC. So the main elements for timescale automatic generation, we think, are three fundamental blocks. So the first element is an efficient and reliable algorithm to steer the scale, and then an appropriate software and hardware, and then some appropriate and dedicated laboratory setup and specific instrumentation we have developed during the last years. So let's first come to the algorithm. This is the high-level structure of our architecture of the timescale generation. So we have the input are the clocks clearly coming from the lab, and then there are also input that are coming from the BIPM, from the UTC data, UTC rapid and UTC. And then, so we have a processing. We have 3 different possible algorithms. steering against UTC rapid, against an ensemble clock, the clock that we have at INRIM, and steering again primary frequency standard, our cesium fountain or the Iterbium clock when it is available. And then we have post-processing and the steering algorithm for that is steering on auxiliary offset generation to produce that is the source of the time, the real source of the time scale based on an hydrogen maser. So we have with this scheme we can run and we are running different time scales. So what is named algo-free is the UTC ET right now, and then we can run a different experimental time scale based on ensemble clock or primary frequency standard steering. Software and hardware. So it's really important to identify the limit of the time and frequency laboratory in our experience and maintain this laboratory, all the network of this laboratory isolated from the rest of the world in such a way that is protected, is safe, and it is not affected if the rest of the institute of the rest of the world network has a problem, has a failure. So we have we did a lot of work in order to realize our own internal time and frequency network, and within this framework there are only the essential part of the time scale generation with our clocks, servers, all the time transfer comparison, GNSS, two-way satellite, and so on, and all the measurement instrument. The rest of the communication to our BIPM, the rest of the institute is done outside this framework, this security framework, security frame that we have constructed in our laboratory. We use a virtual machine architecture because it's easier to implement, and it is easier to update, upgrade, and if you have to replace, it's all based on virtual machines, so we don't have a real machine. We have a certain number of servers. In the present, we have 4 servers where the virtual machine are loaded on these servers. And then we have all the data that are shared on NAS or other type of magnetic support. So this is a very flexible and robust architecture and easy for maintenance and for fast recovery in case of failure, because you have to only reboot a virtual machine is much easier than rebooting a real machine. Wait, oh, sorry. Okay, then the software architecture. We kept the architecture of the software as modular as possible, in such a way that if we have to change one module of a system, it's easier and we don't have to redo all the software. So this is allow for faster development and is deployable with a flexible configuration, and much easier to replace and substitute part of the software if this is needed. The algorithms are implemented in a scientific program, MATLAB, and then are executed with Linux scripts. So let's now come to the laboratory setup and instrumentation. This is the setup that we have implemented in the last few years to allow for a robust generation of the time scale. So our configuration is we have 2 independent in our laboratory. We have 4 hydrogen maser and 4 cesium clock. And these are used for the generation of the ensemble time scale. For the generation of the UTC ET, right now we are using only 2 hydrogen maser, 1 master clock and 1 backup clock. And we have each clock is connected to a AOG, that is auxiliary offset generation. So basically it's just a high resolution synthesizer that takes as an input the clock frequency and generate the 10 megahertz with the proper offset, so that we are able to have an accurate frequency, and we are able to change the frequency if we need to change the frequency. And then we have a second system that is the backup time scale. And the two time scale are continuously compared in a unit that we call a switch, that was custom developed by our colleague Marco Siccardi. It's not a colleague, it's our friend Marco Siccardi that has his own electronic company. So this is a switch that is continuously comparing the master time scale and the backup time scale, giving us continuously the phase difference between the two time scale, in such a way that we can monitor, we can change between the master time scale and the backup time scale if we need. The switch is capable of switching between the two time scale without a significant phase jump. The phase jump, when we have a switch, is contained within a few tenths of hundred of picoseconds. So the backup time scale is automatically aligned with respect to the master time scale daily, and we have developed a dedicated script so that in case of switching, we have a minimum phase and frequency change between the two time scale. Now we have both. We have a first prototype, and we have also a second prototype with some improvement. And in this way, we are able to continuously monitor the time difference between the two time scale. So the output of the switch, the 1 PPS output of the switch, is the official UTC reference plane, so that when we have to change between the master clock and the backup clock, we don't change the reference plane. So for the UTC, this change is almost transparent. We can change either because we have to do some maintenance, some programmed maintenance of one branch of the master or the backup, or because we have a failure. So how work this system? The generation of UTC ET is, as I said, is based on a virtual machine architecture. So the virtual machine make a pre-process of all the hourly clock data that are taken in the lab. So we have a dedicated measurement system that does all the measurement and comparison of the clock signal. It's all the PPS generated by the clock are compared one with respect to UTC ET hourly. So the algorithm make a pre-processing of this data, compute the frequency steering correction for the master and the backup clock, compute the correction to keep the backup time scale aligned with the master time scale within 200 picoseconds. And then provide the command for the auxiliary offset generator implementing the frequency correction. Then, if there are some automatic alarm thresholds that are achieved, produce also some alarm and provide alarm to the technical people of the laboratory. So just to give you an example of one check alarm, when we compute the correction, we have a step of 200 picoseconds, as I said. And then if the computed frequency correction is larger than a given threshold, we the correction, if it's smaller than a given threshold, the correction is automatically applied. If the difference is larger than a given threshold, this means that there is some problem either in the master timescale or in the backup timescale. The system automatically is not capable of saying if the problem is in one scale or the other, in the master or in the backup timescale. So no correction is applied and the alarm is raised. So the people, the technical people is alarmed and come to the laboratory and decide if the problem is in the master timescale or in the backup timescale. If the problem is in the master timescale, turn the knob of the switch and switch to the backup timescale, and this switching is performed automatically. The automatic switching between the master to the backup timescale happens only in case of extreme failure, let's say. So if for some reason the master clock is switched off, for some reason has no more signal, is switched off, we have an automatic switching to the backup timescale. Otherwise, it's always something that is done by the operator. Then we have developed also a series of written procedure in case of issues, so that we can maintain and repristinate all the level, because we have since continuously running a system, we have different people that are asked to intervene in the laboratory and to solve the problem. And so not all of them has the same degree of technical confidence with the system. And so we have important documentation for doing all these activities. And then we have a lot of automatic monitoring. We are monitoring a series of important series of parameters that are daily sent to the operator, to the people that are responsible of the generation of a time scale. Like, for example, you can see here the frequency measurement of our hydrogen maser 4 and hydrogen maser 2 with respect to the fountain, or the comparison against other UTC in real time. These are data that are provided by two-way satellite time and frequency transfer. And so we can easily, we have many eyes that daily can check this data. And so we can easily detect if there is some anomaly. And so we can detect where is the anomaly coming from, and we have to plan some non-automatic some operator activity on the time scale. So coming to the conclusion, so UTC ET is fully automatically generated since more than 1 year, and two hydrogen maser are independently steered versus UTC Rapid with the present configuration. We decided to use this steering against UTC Rapid because we know that UTC Rapid is always available, while, for example, the steering against the fountain and the primary frequency standard is, even if it is more performing from a timing point of view, it requires a much bigger effort to have a continuous operation of a fountain. And even if we can, we had an uptime of our fountain in the last year that was quite important, it happens that you have some days or week when the fountain data are missing. So we decided for the automatic generation of UTC to use the UTC Rapid as a steering reference. Then we have developed software and dedicated software and hardware, a dedicated modular software to have high flexibility. And then we have developed a virtual machine architecture from the hardware point of view to improve the robustness and reducing the maintenance complexity of the infrastructure. We have an automatic alert and monitoring system that produce some files that are sent by mail to the operator every day. And then we have developed this switching system that allows to perform a lot of maintenance activity and provided a significant increase in the robustness of our system and the reliability of the timescale. Right now, as I said, we have 2 timescales that are realized in real time, and then we have different other timescale that are, how to say, experimental timescale that are being studied with different sources for steering. Thank you very much, and it was really a pleasure to have this presentation to the CCTF workshop.
Thank you very much, Filippo. Very interesting presentation. I know I have a lot of questions that I'll have to follow up afterwards about the details of your virtual machine setup. And that's very interesting. Probably what all we should implement to save on the hardware we're using for redundancy. I see a question from Andreas.
Yeah, good afternoon. Filippo, very nice talk and very interesting information. One thing I was missing to understand, maybe you told it, I didn't get it. The switch that you use by Marco Sicardi, does it autonomously switch the PPS and the 10 megahertz?
Yes. Yes.
And also, so when you assure the phase coherence between the PPS,
yeah,
the 10 megahertz is also assured.
Yes, yes. To be honest, Marco kept quite secret the way of the architecture of his switch. My suspicion is that there is inside an oscillator, and so it provides some type of phase locking of his internal oscillator with respect to different input, maintaining a fixed offset so that it measures continuously the offset between the input and it provides some the output in a coherent way. This is my suspicion, but it's how to say, it's an industrial secret kept by Marco. So.
Okay, because I was looking for a device like this. We had once upon a time with the PTFs for Galileo, and then this is the single point of failure in your chain.
Yeah, absolutely. Yeah.
And this we were not allowed to do. So okay, thanks.
Yeah, thank you.
I don't see any more questions. So thank you, Filippo, again. And we'll switch to the presentations from Jeff Sherman. Please, Jeff, share your screen.
Hello, good morning from Colorado. Please let me know if the screen is not shared correctly. I think I'm in full screen mode. And please just interrupt if something technically is going wrong. Thank you for the invitation. Before I start in detail, I'd like to summarize that there's been some reorganization since 2019 or so in the NIST Time and Frequency Division. Elizabeth Donnelly is now the division chief, and a sort of super group has been aggregated, centralizing all the activities related to UTC NIST generation and distribution. The group leader is Mike Lombardi. I won't read the list of names, many of whom I think you're familiar with, but I'd like to introduce some of our new staff and also provide you current contact staff for various critical operations. So those are listed here for your reference. Besides all the chaos in this country that has made international news, I'll tell you about some more that's more local to NIST. In the last 2 years, we've had many more than 20 power outages on the campus. Many of them are quite brief, but some have been extremely long and have been catastrophic hardware failures at the high voltage power feed. In addition to these spontaneous failures, in this year alone, our building infrastructure folks have scheduled 4 planned days with greater than 12-hour site outages planned so they can upgrade old hardware. And unfortunately, we have to cope with all of these things. The UTC NIST generation hardware is spread over 2 buildings on our campus and about 7 or 8 rooms. And some of the rooms haven't been renovated in 20, 25 years, and the hardware for controlling temperature and humidity is not so great. Here I plot not the worst example and no catastrophic failures. This room is just not all that well regulated or all that well regulated to boil. So we have to cope with these situations day in and day out. We've spent quite a lot of effort trying to engineer against these sorts of failures, and we find that schemes to provide redundant power sources are incredibly useful. There's an amazing number of uninterruptible power supplies, both large, high current building scale supplies, and also the small sort of 1 to 2 kilowatt supplies that you can commonly purchase and deploy yourself. I found incredibly useful the so-called rack-sized automatic transfer switches. These protect against circuit faults, but also it allows you to sort of move racks across the room and bridge between different outlets. You may find they're incredibly useful and only a few $100 American. We deploy 2 diesel generators and automatic transfer switches and dedicated circuits for our group that is independent both from the life support, like air and emergency lighting support of the building. All of our atomic clocks have DC battery backup. In particular, the hydrogen masers will live for about 10 hours on their batteries, and we cycle all the batteries preventatively on a 2-year rotation schedule. We've also engineered several other devices to be on a 3rd battery backup system that includes all the clock measurement systems, monitoring systems, distribution amplifiers, both at 5 megahertz and the pulse per second, the offset generating synthesizers, pulse per second generators, and to any extent possible, any of the distribution services that are digital. All of our rooms involved have at least 2 built-in cooling methods permanently mounted to the ceiling somehow, and at least one of these is backed by one of these diesel generators. We also own some portable air conditioning units, the sort you can buy at a hardware store, or the sort that require cold water for heat exchange, and they can cool more like 7 kilowatts of heat transfer. The lower power ones just plug into the wall, and we move them around in the case of emergencies or where extra cooling is necessary. And in our newer building, the clocks that are inside of environmental isolation and control chambers, those are UPS backed, but in all cases, those chambers are generator backed. So at most they see a few seconds of power loss, and they either die because their motors don't like power loss, or they come back and temperature control is mostly seamless. Generation of UTC NIST is outside the scope of the talk, but it's an ensemble timescale. There are about 21 clocks, hydrogen masers, and cesium beams, although not all of them receive weight in the ensemble, and not all of them are reported to the BIPM. We try to choose only the healthiest clocks to participate in the weight of the timescale and to be reported. But having made those choices, we implement the measurement and the generation of UTC NIST redundantly. So here, for example, in red are measurement systems and the output synthesizer, which are considered the primary output, and the blue is an alternate drawing from the same population of clocks. These timescales are generally kept to within 50 picoseconds of each other by a steering algorithm. The data there shows the result of a time interval counter measurement between the pulse per second of the backup versus the primary, measured actually after 1,000 feet of cable delay. The blue data shows the quantization of the time interval counter. The black data is a windowed averaging, and the entire span of the plot here is something like 400 picoseconds. In a real emergency, we also have one synthesizer directly tied to a clock that can be manually adjusted, for example. And in the current implementation, there's actually 4 of these, 2 in a new building with a different population of clocks. And ultimately, we'll want to transition to that as the primary. But in the meantime, we run all 4 of them with delays and alignments monitored so that when we make the transition, it should be seamless to folks like you outside the building. And in the meantime, those serve as independent backups. In a sense, they're in a different building, they have a different population of clocks. So the walk-off dispersion is greater, but it's another independent check we use to actively judge the health of UTC NIST as broadcast. There are, of course, switches for us. We choose independent switches for pulse per second and the 5 megahertz. And our switches are not that fancy. They are so-called break before make. So although the phase continuity is ensured for the 5 megahertz before the switch, actually flipping the switch drops cycles for downstream users. So it means that the two-way satellite modems, GPS receivers, downstream synthesizers all become unlocked. And we have a list of people that need to be notified to resynchronize their systems in that event. I think it must be the case that any switch that does better than that has a dual phase lock loop control, which adds its own complications and potentially noise. So it's a step we've not chosen to take, although I think it's a good one. Finally, I mentioned that our hydrogen masers especially, and most of our cesium clocks are isolated from our poor room temperature and humidity control in these purpose-built so-called environmental chambers. But I hasten to add that it's not all roses. It's a double-edged sword in that these things add cost, complexity. They have their own failure modes. And for example, when they fail, they turn into an insulating box concentrating heat, meaning that their failure requires sort of rapid response to protect the clock that's inside. So redundancy comes at a cost, and it's not always worth doing everything that is imaginable. To control this chaos, we have deployed about 25 purpose-built microcontrollers for measuring temperatures in rooms, temperatures in chambers, humidity, whether power sources are live or not, and in a few cases, magnetic field. We also implement microcontrollers as so-called read-only serial interfaces. In other words, we don't want to connect the maser data stream to a general purpose network because we don't want anybody, either by accident or purpose, to be able to program the maser to steer a frequency correction. So the microcontroller is only told how to query data and pass it upstream. And we choose for this a daisy chainable serial bus, but it could be something else like Ethernet. In fact, we employ Ethernet both on a controlled segment of the NIST network to monitor time interval counters, or on our private network where we literally string Ethernet cables ourselves, keeping it out of the hands of NIST IT administrators. Although they're good-natured, they implement reboots at 2 a.m. on Saturdays that we don't want to experience. We also deploy so-called industrial relay controls that sense things like power quality, or sense whether our generators have started or backup cooling has come on for any reason. And that's all aggregated in monitoring an alarm system. The primary purpose of the alarm system is to record the data, and on any excursions defined on the next slide, to command a microcontroller to dial a real physical modem that's connected to a real copper phone line, not a internet-enabled phone line. And this dials one way or another a cell phone network of a bunch of humans employed by the division. And I highlight in red a feature where if this microcontroller is not reset every 20 minutes or so, it dials the modem all on its own to the same list of actors. And this is to test whether the aggregation computer has crashed or suffered a reboot, or for whatever reason has lost communication. Also, the data is stored in various formats on a network. Emails go out, and in addition, the computer knows how to talk to various chat apps like Slack or WhatsApp, could be done in Principal or Microsoft Teams or what have you. And these are ways that data gets out to the appropriate user about the system. Here's just a screenshot, and I'll summarize some of the qualities. The software is a compiled LabVIEW executable. This is an option that I think is worth doing. It seems to make the deployed application more stable when you run it as a compiled executable. You don't get nagged about upgrades. Drivers don't upgrade underneath you, suddenly breaking your software. And the software was implemented in a way that handles native LabVIEW errors, even if they're unexpected, those errors are turned into alarm messages so somebody can go and look and see what the bug is in the software without the software crashing unexpectedly. At least that's the design. There's very little hard coding. The configuration is done at runtime with text files or queries to a database. So we don't often have to recompile the application. There's no plotting. We do that separately. The data is simple text files. We wanted to keep the alarming as simple as possible. And again, this thing tests the alarm daily. And if it were ever to crash within 30 minutes, the microcontroller will dial the alarm system for us. Just this morning, we had an alarm. So this is a screenshot of an example. There's a key green light that turns red. So at 2 a.m., it's easy to see something's wrong. And there's some data given about what sensor is wrong. And if it truly is a false alarm or benign, there's an exception button that lets us silence the alarm and deal with it in the morning like a civilized human. We categorize the errors in terms of severity. I won't go through the list, but the most severe errors we immediately alarm on, and the shortest measurement interval is 12 minutes. So that's the maximum delay for these most critical errors. For example, an apparent step in UTC NIST. There's several other alarms that either have to occur twice in a row, or it's a measurement system that runs on a slower aggregation interval, like 30 minutes. And for example, conditions that affect a single clock, we have a more relaxed criterion. And less severe results are aggregated and sent as a digest for that daily test email. So we learn about perhaps looming problems that haven't risen to a high degree yet at the end of every working day. Finally, I have one comment. I think this describes a general flow where researchers might make measurements about clocks or GPS reception or the two-way satellite time transfer, and more or less send this data to the BIPM for consumption. But oftentimes we take data and store it in a different format than the format that's ultimately sent. And firewalls seem to cause a lot of chaos in, or firewall changes anyway, cause a lot of chaos in the transmission of this data. So at least I think the best practice involves something like this, where a monitoring system ought to re-download any emitted product and apply additional integrity checks. For example, you can see that the files exist and you must not be fooled by named files with 0 bytes in them, which is a particular failure mode of FTP. You should also investigate the contents of the file, and you can't really rely on modification timestamps for the same reason. So some kind of hash function is a useful method of doing so. And also has been mentioned by other talks in this session, it's good to not assume anything about the data, but perform very basic tests. Are timestamps increasing monotonically? If you take first differences between successive timestamps, are they smooth? One can implement these tests without really knowing what the original data looked like. And these are tests that could be implemented by a student or a researcher that doesn't have so much experience, because essentially they're just implementing sane questions about data streams. And the alerts can then be dealt with. The tests can be refined if there are too many false alarms, et cetera. So in general, I think this is best practice. It's not uniformly followed at NIST because all of these processes are implemented by individual researchers. But if we have the opportunity to re-engineer them, I think we'll apply these principles. So in summary, we try and prepare the most robust systems we can, but we appreciate that adding redundancy costs. It costs money, it costs time, it costs labor, and crucially, it costs simplicity. These systems can become an infinite Rube Goldberg machine of headaches. We tend to try and measure and record everything, but we are very careful with what we alarm. It's very expensive to wake up a human at 2 a.m. So we try and do that at the minimum level. We also consider failure of the alarm system to be the most serious alarm. So we try and learn about those failures at least daily. Finally, we try and have a full circle check, like many of the other speakers have implemented, checking the data that actually goes out of the laboratory in some independent processing stream. So finally, despite all that's been in the news and with COVID, Boulder is still a nice place to visit. I recommend you come if you can when travel becomes available again. thank you again for the invitation to speak. I thought there were lots of interesting things discussed in this session. I was very eager to hear about other practices, and if there are any time for questions, I'd love to take them. Thank you.
Thank you very much, Jeff. That was a very interesting presentation. Somewhat reassuring that even better funded laboratories face air conditioning failures and mitigation strategies for that. I'm sure we're all familiar with that. I have a quick question. The microcontrollers that you use everywhere for telemetry monitoring, you mean Raspberry Pi computers?
No. No, I suppose I wouldn't choose something with a general purpose operating system. However, something as simple as the cheapest Arduino style microcontroller with as easiest a development environment is more than sufficient. Most of our microcontrollers were built by people who really loved microcontrollers, so they chose to make custom printed circuit boards. They chose to do all the implementation of the microcontroller support chip. They chose a PIC style microcontroller from Microchip Incorporated, but the Arduino style is much more accessible. There's a lot more online support to teach you the tools, and I would recommend that if we were to redo it or if anyone else would like to do it. I think there's maybe nothing wrong in principle with the Raspberry Pis, but it seems like the SD card and flash is a failure point. The fact it's a general purpose operating system may frustrate your IT managers. Our IT managers don't like uncontrolled general purpose operating systems.
Okay, thank you very much, Jeff. Yeah, exactly. Very, very good points. Thank you. Any more questions? I don't see any hands raised. Okay, well, I would like to thank all the speakers for the excellent presentations. I think there were a lot of very useful ideas presented today on how every one of us can improve our operations and benefit maybe from already developed solutions. And that's the idea of our working group, is to share as much information as we can, including solutions, to improve the time and frequency community of overall operations. I will share my screen now for a few concluding slides, and maybe at the end we'll open mics, and I hope at the end we can take a photograph of the participation. So I'll just share my slides. I know we're running a little bit late, so I thank everyone who can still stay at the meeting. So what are the next steps? We heard today many presentations about the issues we face with the calibration of our receivers, with data quality, with different solutions on how to improve capacity, how to improve operations of the labs. So we want to keep these activities live and allow everyone to benefit from those. So what can we do to enhance further the training and knowledge sharing? So focus on better UTC key realization, data monitoring, validation, and calibrations. That's the goal for our working group. Establish long-term program that will allow regular training via summer schools or workshops, for example, and that the materials for this training program will be continuously updated based on the resources being developed by individual NMIs or for this purpose. An active website with resources for training and sharing, which already is in existence partially, and we can benefit from it. And training, of course, in-person training, hopefully at peer labs or second year BIPM that Patricia has mentioned. So we have examples for launch of the BIPM new e-learning platform that was already presented in the talks today by Patricia, Aurelie, and Yuko, I think. So can we make use of this platform to add web pages specifically for time and frequency knowledge sharing, where we can post questions have a forum-like platform, post links to software tools, phones, presentations, and training material from tutorials and conference that we have already available. The second deposition that Patrizia mentioned earlier for the PPP, IPPP development, that's one of the second depositions, but also there is a possibility to have a specific one to focus exactly on the development of the training program and the knowledge sharing platform. There are funding sources available. And for example, the IEEE UFFC Society is interested in funding a summer school or other training activities, specifically in the domain of time and frequency metrology. And we can benefit by leveraging their funding and our own and BAPM resources to make this training program a reality.
Maida, do you want I use my local version to be shared?
Yes, please, Patrizia, because mine is blank. I have to restart the computer.
So I think this is the slide you wanted to show.
Absolutely. Thank you very much, Patrizia. So specifically, what needs to be done, and this is where we are looking for active participation from TI members, including filling the second D position at BIPM to actually focus on this development. Some of the points were already mentioned by Yuko, but we need to identify the courses, topics, and materials for training, identify experts and lecturers, collect available resources, prepare new materials for training, and share software to use, organize and support the collaborative platforms for training and resource sharing. There are different ones. Organize training events and research and regional metrology organization technical committee meetings and at conferences. Apply and organize funding, and I'm sure there are many more activities that I missed that would allow for all this effort that we're putting in individual individual NMIs and DIs to benefit the whole community and therefore multiply in efficiency. So action is needed from TI members. You can volunteer. You can volunteer with your NMI's employees of your NMI funding, and please contact BIPM and contact working group, TI, myself, with suggestions what you can do and how you would like to help with that. Patrizia, the next slide, please. This is the slide about this meeting. The information for the meeting, the presentations will be available on the BIPM website. There are a lot of interesting details and presentations that we have seen today. So please make sure you go onto the website. If you haven't done that before, you will have to register, and there are instructions on how to register. You have to sign in, set up a password, and so on. It's relatively straightforward. I've done it myself, and I didn't need to call BIPM for help and rescue. This concludes my remarks. What I want to say in general, thank you all for participating in this meeting. And despite COVID restrictions on travel, that we cannot meet in person and see each other and have informal chats and maybe more active question and answer period. I think this virtual meeting gives an opportunity to have many more participants from many more labs attending the meetings. And so I think this is great. And I invite you as individual labs to suggest maybe small working meetings on specific subjects when you can invite individuals that you want to ask questions or to meet virtually, and let's have the network running actively. If you want contact information for anyone, you can approach Patrizia or myself, and we will be able to help you connect with the individuals that you want to reach out to. So I would like to invite you to maybe ask questions or make comments if you want right now before we close this meeting. So again, I will ask you to please use the hand raise option, so I can invite you to speak. That's the disadvantage of the virtual meetings. People more shy. They don't they don't raise hands and ask questions. But I see there are comments in the chat that you're welcome to read as well. And since the conference is recorded, any questions in the chat will also be saved. So that will be an opportunity for us to review the questions afterwards if they come. Well, I don't see questions coming, so I want to thank everyone. And Patricia, maybe you can take. Oh, Oscar has a question. Good.
Thank you. I see that we are recording the session. Maybe for some colleagues, it would be possible to ask to the presentation to the video for the people to see the presentation, or this is private?
Usually we record just for the possibility to know what we have discussed and if there is any action. So it is private, but we can see what is necessary and we can arrange or something. Important is that you give us the presentation, so they will be available on the web page. And I think this is already an important issue. Then if video is needed, we will need to ask to the speaker the permission to give you the video.
Okay, thank you.
If you can switch on the camera, we will take some pictures, so we will have a picture of the meeting, which is in a virtual way, but is what we have.
Thank you, Patricia. So will you be taking pictures?
Yes.
Okay. We had 94 people at the peak of the attendance, so I think this is great. So we have three screens of images.
Yes. Yes, thank you. So that the picture is ready. I would like to thank you for the participation. It is really nice to see the name that I know, because I have seen your name in some mail, but I have never seen your face. So it's very nice to see you. Other faces are more known, and it is always a pleasure to see you. The next CCTF will be in June 2022. We hope to be able with Marina to have this meeting in person at the BIPM. Don't forget to send me your presentation, and it will be in the next days on the web page.
Thank you all very much. And this closes our meeting. And maybe we'll have another virtual meeting between now and the next one at June 2022. We'll see. It's great to see you all and be in touch.
Okay. Bye.
Thank you. Bye.
Bye.
Bye-bye.
Bye.
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 Bye-bye.